This video is starting chapter 12, unit 4, talking about sound waves, more particularly looking at intensity and the equation that goes along with it, as well as Doppler effect. First thing is a review of types of waves. So our vocab here is going to consist of compressions and rarefactions. Remember, compressions are like the crest on a sine wave, whereas rarefaction are like the troughs on a sine wave. Furthermore, compressions are going to be areas of high pressure. That's when your waves are going to be squeezed together, whereas rarefaction is when the waves are going to have a lot of space in between them. Therefore, the molecules are going to be under low pressure, so you'll have like lower frequencies, lower sounds, lower pitches at that position. So once again, guys, let's kind of look at what a type of wave a sound wave is. A sound wave is going to be a longitudinal wave. So this picture up here is denoting what a longitudinal wave is going to look like. And then this picture down here is looking at what a sine wave would look like. A sine wave that is generated from making a longitudinal wave. So it's kind of like who crossed the road first, the chicken or whatever. Anyways, the longitudinal wave came, and then you make the sine wave from the longitudinal wave. Yes, I am tired. It is 8:30 at night, and I'm finally getting around to making your video. Okay, so anyways, let's put some words here. First thing is compressions. So your compression is going to go on a longitudinal wave, or is compression going to go on a sine wave? Well, the word compression should go on a longitudinal wave. So one other thing I'd like you to add here is that you're going to have dark fringes. We'll talk more about this in later chapters like 13, 14, 15, which means down here will be light fringes. And this is associated with your longitudinal wave. These dark areas here obviously coincide with what, guys? The dark areas. They coincide with what area on a sine wave? Well, that area is going to be the crest of a sine wave. Okay, so this is where you would see your crests. So based off of your crest, that's going to be areas of compression. So crests have compression. I'm going to turn that to the side though, because where you have your light areas then, your light areas, right here, right here, right here, are going to be equivalent to what part of the wave? Well, that's called the trough. So looking over here, a trough is known as rarefaction. So a trough on a sine wave is rarefaction on a longitudinal wave. So this is areas of rarefaction, wherever you would see those bands. And then I just threw a couple more in here so you guys could put them wherever. Not really honestly necessary at this time. I think you get the point. Okay, moving right along then. Sine waves. So in the last chapter, sound waves. In the last chapter, we talked about longitudinal waves and transverse wave, in which longitudinal waves, the particles are vibrating parallel to the direction of motion, and in transverse waves, particles are vibrating perpendicular to the direction of motion. So with that in mind, sound waves are longitudinal waves. You should remember that because we had our quote-unquote space phone that we used in class where I had two of your classmates make a transverse wave where the cord went up and down and up and down. You really didn't hear anything. But when we dampened, stopped, put friction into the system, and coiled a couple of it up, the cord, and then let go, you could hear that wah sound coming out of the cones on both ends. Therefore, sound was traveling as a longitudinal wave. So, once again, I would like to just denote the word parallel here. Hopefully you guys can understand that without me having to write too much more on that. The particles are vibrating parallel to the direction of motion, hence longitudinal wave. Whereas transverse would be particles are vibrating perpendicular to the direction of motion. Okay, so which direction are vibrations headed in comparison to the direction of motion? Well, lucky you, you get to write it again, parallel. Okay, looking at this once again, you know that the top is your longitudinal, the bottom is your sine. So we have crest, which is comparable to compression. We have troughs, which are comparable to rarefaction. We have areas of low pressure for rarefaction, and we have areas of high pressure for compression. So if you can get that all squared away, you're doing good. All right, hearing the sound waves. Audible sound waves. These are sound waves that the average human ear can hear. Sound waves that the average human ear can hear. The range is from 20 to 20,000 hertz. Infrasonic. Infra is before, sonic is sound, okay? So think about like Roy G. Biv, visible light. On the EMS, electromagnetic spectrum, what range is right before visible light? Why? That would be infrared, right? Because it's before red in the electromagnetic spectrum, more particularly the visible light portion of the electromagnetic spectrum. So what do you think ultrasonic means? Well, ultra means after, right? Well, what's the last color in Roy G. Biv? Violet, hence it's called ultraviolet rays, UV rays. Science makes so much sense. Okay, so infrasonic sound waves. What range do you believe that is going to be below if you're talking about infrasonic sound waves? Well, that's going to be below 20 hertz. Common sense should then tell you that ultrasonic sound waves are going to be above or greater than 20,000 hertz. All right, next thing that we have then is pitch. Pitch is defined as measure of how high or low a sound is perceived to be. Measure of how high or low a sound is perceived to be. It is determined by frequency. So just like inertia and mass were best friends, inertia and mass were best friends back in chapter 4 in unit 2, frequency and pitch are going to be best friends. So in other words, frequency and pitch are directly related to each other. In other words, they are proportional to each other. So if frequency increases, pitch is also going to increase. Speed of sound depends on the medium. Well, if you have a medium, then that means that we need to talk about mechanical waves. So then it should make sense that sound waves are mechanical waves. A more complete sentence to show your knowledge here would be that sound waves are longitudinal waves that require a medium, hence they are called mechanical waves, in which we can measure and graph the sine wave based on areas of compression and rarefaction. If you can follow that statement, then you're doing great, guys. Okay, although sound waves can travel through solids, liquids, and gases, they travel the best through gases. That should make sense because that's the one where you can compress the molecules or you can pull them apart, those areas of rarefaction and compression. So it should make sense that gases are what sound waves are going to travel the best through. Think about the heat of the day versus the cold air in the morning. You can hear birds chirp and see the bird chirping in the cool morning. Well, like in the afternoon time, or when you like get home from work or school or whatever, you can probably hear birds chirping, but you can't really see them, right? Because those sound waves can travel so much further as temperature increases. So, 2 videos I'd like you to take a moment and watch are when does sound travel faster in gases? This one is totally cool. It's a Rubens tube experiment that you will never try to build on your own. Okay, never ever try to build it on your own. Just watch the video. The sonic boom is awesome because it actually shows you like graphs of the compression of air when a fighter jet, I believe is what they use throughout that video. Sound waves travel away from a vibrating source in all 3 dimensions, X, Y, and Z. So in other words, if we were in the classroom right now and I was speaking at you directly, the students to the left, right, behind, in front, if they were above, if they were below, would be able to hear my voice projected. So sound travels in all 3 dimensions, X, Y, Z. A wave front also looks like a bullseye when you draw it out. Furthermore, this is like the Earth. Sorry, let's try that again. Oh my. Heliocentric. Here is the sun, and here are different orbits of planets going around it, just trying to get you to think large scale. So then you take a snapshot of this right here. So take a snapshot, and now these rays seem to be parallel to each other. Or over here, they definitely were not. They're spreading out in all directions. Agreed? So one thing I want you to know is that rays seem to be parallel. Shocker there that they're parallel to each other when drawn closer to scale. Okay, Doppler effect. Please take a second and jot down the definition of the Doppler effect. I'm still going to talk while you're jotting that down, but please jot that definition down. What we're looking at here is, there's two observers here. There's observer A and there's observer B. Observer A, you can obviously tell that this wavelength is much shorter than observer B's wavelength. So thinking about the equation, velocity equals frequency times wavelength, the velocity is obviously going to be your constant. So the relationship between frequency and wavelength is an indirect relationship. So therefore, observer A, you have a smaller, shorter wavelength, therefore you're going to have a higher frequency. The sound is going to be much louder as it's approaching you. Okay, so the complete opposite of that, since you have a larger, longer wavelength, that means you're going to have a lower frequency. Once again, your velocity is your constant throughout this problem. Okay, when can the Doppler effect occur? The movement is relative motion. So from whom's from whom's perspective are we looking at this? For instance, weather, Doppler 5 radar or whatever would be a good case of where you would see the Doppler effect. Intensity, the rate at which energy flows through a unit area perpendicular to the direction of wave motion. So the direction of wave motion. The units are going to be watts per meter squared. The equation, you cannot abbreviate the word intensity, because if you do, that means I, which is current measured in amps. Intensity equals power divided by 4 pi r squared, in which intensity is watts per meter squared. Power is P, and it's measured in watts. Radius is R, and it's measured in meters. So make sure your variables make sense. Here's our sample problem. The intensity when you're at a distance, it's obviously circular, right? Because it's going on in all directions, so it's really called radius. 3.2 meters. The power output is 0.20 watts. What is the intensity? Once again, write out the word intensity. Do not just abbreviate it I. That is wrong. The equation that you want to use, intensity equals power over 4 pi r squared. Nothing needs to be changed. We got meters, we've got watts, so your intensity is the way it is. We don't need to rearrange the equation. Please get your calculators out. 0.20 divided by 4 pi times 3.2 squared. Okay, make sure it's just the 3.2 that's being squared. Putting that into your calculator, you get an answer of 1.6 times 10 to the negative third. Therefore, your intensity with sig figs, you only want 2 sig figs, happens to be 1.6 times 10 to the negative third watts per meter squared. Okay, there's your final answer. Here are your answers to your practice A problems. Please make sure that you have the appropriate number of boxes to be checked tomorrow by your sub, okay? Mr. Anderson's going to check your boxes for you, so please make sure you box the right answers. I know you can't see the bottom here. It says I equals current measured in amps, so do not abbreviate intensity, okay? So if you put I equals, it is wrong, guys. Please do not do that. Okay, next thing that we have is 2 factors that determine which sounds are audible. That would be intensity and frequency. I'm going to stop right there. Practice A is your homework.